Now we will discuss about torque acting on a current loop. Consider a rectangular loop like this, carrying a current, say I. So let us call this as, say, P, Q, R, S. Let A be the width of the coil, that is width of the loop, and say L is the length, or say, let us say we call this as B. B the width of the length of the loop. So A is the width, L is the B is the length, and this coil is kept in a uniform magnetic field. Suppose these two are the magnetic poles of a permanent magnet producing uniform magnetic field. So the magnetic field direction will be like this. So this magnetic field produces a force on the current carrying coil. You know the formula for the magnetic force, that is VIL sin theta is the general formula we derived, where V is the magnetic field, I is the current, L is the length of the conductor, and sin theta, that theta is the angle to the direction of the magnetic field and the current element. So in this case, the plane of the coil is parallel to the magnetic field, or we can say the magnetic moment of this coil will be actually perpendicular. So that the magnetic moment exactly will be perpendicular to the plane of the coil. So you can say in this case the angle between the magnetic field direction and the area vector, so that will be pi by 2 or 90 degrees, hence that will become, actually sin theta will become 1. So the current element, you observe this here, in this direction, magnetic field is like this. So the angle between the current element vector and magnetic field vector will be 90 degrees. Therefore, these sides PQ and RS will experience a magnetic force, but whereas these sides QR and this PS will not experience any force because the magnetic field direction and current direction is same. So therefore we say that the sides, that is PS and QR doesn't experience magnetic force. Okay, only these sides PQ and RS, PQ and RS experience the force. So therefore force on PQ, that is this force on PQ is equal to magnetic field strength, current in the conductor, and here I have to take the length of this conductor, is say some B. And similarly force on this side RS is magnetic field, current into, that is the length. So these two sides won't experience the force because field is parallel to the current element. Hence this side and this side won't experience, but whereas the sides PQ and RS will experience. But see the direction, the magnitude of the force on PQ and then RS is same, but their directions are different. So, according to our right hand palm rule, so this is the conventional current direction, this is the direction of the magnetic field, draw the normal. So, that will be into the plane of the board, and whereas on this it will be out of the plane of the board. So, let us call this as force 1, let us call this as force 2 for convenience. So, we represent this as force 1, F1, and we call this as force 2. Both are equal in magnitude, but their directions are opposite. That is, the force, so let us say this is the magnetic field, the force on this will be into the plane, whereas the force on this side will be out of the plane. So according to our right hand palm rule, it will be outwards, here it will be inwards. So that is F1 is equal to F2, but opposite in direction. Okay, so if suppose if this is the coil, the force on this is say F2 on this side, and on this side it is F1. And you know the magnetic field is perpendicular to the direction of the current in the conductors, and hence let us say suppose this is the magnetic moment or M bar, and from this let us suppose this is the side at a distance, that this side is at a distance a by 2, this side is at a distance of a by 2. So the distance, the perpendicular distance between the lines of action of the force will be a by 2 plus a by 2. Therefore, the resultant force, F resultant, if you observe, is 0, because both forces are equal in magnitude but opposite in direction, acting at two different points. If you consider this is the center of the coil, since these two forces are equal in magnitude and opposite in direction, they cancel out. So the resultant force is 0, but the effect of the forces is not 0. And you know this magnetic moment is the magnetic moment produced by the current carrying coil, not by the external field. And your external field is like this. This is the magnetic field direction, and that is perpendicular to the magnetic moment of the coil. Okay. So therefore here resultant force is 0, but the effect of the force is not 0. They constitute a couple. So the forces will try to rotate the coils about this point O. So it will rotate about this point O. So the torque produced by the couple of forces is given by force into perpendicular distance, and the point about which it is rotating. From that point, so if A by 2 is the distance, we can write like this. But this is nothing but forces are same. Hence, F into A by 2 plus A by 2. So, here we consider this as say some F. Therefore, I took that as common. So, F into A by 2 plus A by 2 is F into A. F is nothing but B, capital B, I, small b into A. So, this is the length of the sides of the rectangular loop, and A is the width. So therefore, this quantity is nothing but area of the rectangular loop. So I can write like this. Therefore, torque in this case is VIA. So that is the formula for torque in this case, acting on the rectangular loop such that the plane is parallel to the magnetic field. Suppose if the plane is inclined to the magnetic field direction, if the plane of the coil is inclined, so if it is inclined, so let us suppose this is how this coil is, and of course at the center the magnetic moment, let it be represented by this. So the magnetic field direction is this V bar. Let us suppose it makes an angle theta with the normal drawn to the area of the coil. So area vector or to the magnetic moment. So if it is making an angle theta, we know that this angle will be 90 minus theta. So therefore the forces acting on the sides, so that is F1, this is F2. Now I want to know the perpendicular distance. So this distance you want to know. So if you observe, so this will be A by 2 sin theta, and similarly this also will be A by 2 sin theta. Okay, therefore the total distance will be A sin theta. Hence the torque in this case is given by F1 into A by 2 sin theta plus F2 into A by 2 sin theta. Okay, so that is equal to F into A sin theta. But what is your F? F is capital B, the current, length of the coil, A into sin theta. So I can write like this. Therefore, torque is equal to BI. So this small b into A is taken as area of the rectangular loop into sin theta. So that is the formula for the torque acting on the coil. If the coil is inclined to the magnetic field direction, and we know that magnetic moment is given by the product of current into area. Therefore, torque can be written as B m sin theta, and therefore in vector form tau bar is equal to, that is m bar cross b bar. So similar to in the case of electric dipole, we derive this formula B bar da cross B bar. So it is very similar to that of electric dipole, but kept in an electric field experiences a torque. So very similar to this. So from this we can discuss 2 points. If the dipole moment vector is parallel to B bar or anti-parallel to B bar, then the torque will be 0. That is, tau is equal to 0 if theta is equal to 0 degrees or 180 degrees. So if it is 0 or 180, that means if the dipole moment vector of the coil is making an angle 0 degrees or 180 degrees, it means if the coil is perpendicular to the field direction, so if the coil is perpendicular to the field direction, then the torque will be minimum. But in terms of magnetic moment of the coil, we can say that if the magnetic moment is parallel to B or anti-parallel to B, torque will be 0, because the coil can be like this if the magnetic field is like this, coil can be like this or can be like this. You see this case. So this is, suppose if it is magnetic moment, suppose this is the direction of a magnetic field vector and this is the direction of the magnetic moment of the coil. This is anti-parallel. So if I say like this is the direction of small m bar and also the direction of the magnetic field. This is parallel, both are parallel. So either in this case, so magnetic field, you have to imagine like this. This is the coil. So the magnetic moment of the coil and the magnetic field are parallel, or here they are anti-parallel. So for these two positions, the torque will be 0 because sin theta, if you substitute 0 degrees or 90 degrees, this is going to become 0. So a position where m bar is parallel to b bar is called equilibrium, stable equilibrium. So if you disturb the coil slightly, again it will be brought back to the initial position. So it is the same position. So that's why it is called stable equilibrium. So again brought back to the same position. Whereas if it is anti-parallel, then a small displacement of the coil, a small movement of the coil will increase the torque. So that is unstable equilibrium. So depending upon the position of the coil in the magnetic field, it may be in the stable equilibrium position or in unstable equilibrium position. And we make use of this formula, that is torque acting on the coil in a magnetic field, to explain the working principle of a moving coil galvanometer. That is the next topic we are going to discuss.